This is part 7 of lecture 11 of ELEC5300. Here I'm just going to give a short review of constrained optimization for those of you who aren't familiar with it or maybe just need a short refresher so that you can kind of understand that Lagrange multiplier step I did in the maximum variance formulation solution. So constrained optimization, what we'd like to be able to do is find the maximum of some function, and the function here is f of x1 comma x2, so it's a function of two variables subject to a constraint relating x1 and x2, which I can write in the form g of x1 comma x2 is equal to 0. Right. So the way you can kind of visualize this is as follows. Well, this is a function of a two-dimensional space, which is described by this direction x1, right, and another direction x2. Right? And so for every point x1 and x2 on this space, I have a function value f. And so you can kind of think of f as being the height of a surface above this 2D plane, right? So I might have something like this. I might have something like a bowl. And so the lowest point in the bowl would be this point here, right? Which I could say, well, maybe this point here is sitting right on top of this point in the plane down here, right? So this direction here is really the direction that's describing f. Right? So f is a function of x1 and x2. Now if I was going to minimize this thing, then I would like to then choose this point here, but maybe that's the unconstrained minimization problem. But maybe there's another point that I want to take into account, is that I don't have free choice over x1 and x2, but instead it's constrained by this equation, which we can see right here, this g of x1 comma x2 is equal to 0. So that might be some kind of line in the x1 or x2 plane, or it might be a curve or something like that. But anyways, let's just draw this one like this. So there's this line here that maybe goes through here. Right. So even though I'd like to minimize it at this point here, I can't, because I have to somehow stay along this line. Right, so this line is the constraint where g of x1 comma x2 is equal to 0. So how might I solve this? Well, one way I might solve this is I can say, well, I know I have to stay along this line. What I could do is just evaluate this function along that line, right? And so how would I do that? Well, what I could do is I could say, well, even though I can write this as g x1 comma x2 is equal to 0, this is kind of not that easy to deal with. So what I could say is maybe I can solve this. Maybe this thing can be written in this form. x2, the direction in this direction, is just a function of x1, right? So this is some function h of x1. So now I know what x2 is, as if I know what x1 is, right? And so now, since f is a function of x1 and x2, I can just substitute h of x1 for x2, and then I just have a simple one-dimensional equation, which just kind of tells me, well, how does the height vary as I move along, let's say this line here, and I just have, let's say, maybe some kind of surface here, and I would just want to then find the minimum point along that surface. Maybe it would be, some point over here or something like that. So I can do this just by saying, well, I'm going to differentiate. This is just a single variable optimization. I differentiate with respect to x1 and set the derivative equal to 0, and I'm done, right? And if you can do that, that will work, and that's a completely valid solution to this problem, right? But there are some things that are kind of not so satisfying about this, right? The first one is that it seems like we made an arbitrary choice between solving for x1 and x2, right? In fact, we did. I mean, I could have easily written something like x1 is equal to some, g of x2, right? And substituted into for here rather than over here, right? So I've kind of destroyed this natural symmetry between x1 and x2 by treating them differently, by making that choice, right? And the other thing is that, well, maybe it's difficult to find an analytical solution for h, right? Like, how can I solve this, for example, if g of x1, x2 is equal to something like this? So suppose that I had g of x1 comma x2 was just equal to x1 squared plus x2 squared minus 4 is equal to 0, right? Well, what is that kind of line or curve on the x1, x2 plane? Well, that's just going to be a circle, right? With radius 2. And so I can't really solve this for x2 in terms of x1 or x1 in terms of x2 because there's two solutions here, right? And you can see there's a very nice symmetry here, not in this particular circle that I've drawn, but anyways in this equation here that I don't want to destroy. So I want to find another way to solve this without having to destroy that symmetry. And so the way that you can do that is use this approach called Lagrange multipliers. And so the first thing to notice here is that the gradient of the constraint function is orthogonal to the constraint surface. So, this red line here might be the surface that I need to stay along in order to maximize the function. So I only want to find a point along this red line, but I want to find the one that makes the function as large as possible. Now, if I look at the gradient of this function g of x, right, at this point x, it turns out that that's pointing in a certain direction, right, either pointing up or pointing down, right? And that gradient then is orthogonal to this surface, right? So if I draw a tangent line to this surface, this line is going to be 90 degrees. How do I know that? Well, one thing I can do is I can say, well, let's look at another surface here, point on the surface here, this one here. And so maybe I'm interested in this one here. And this is this motion from here to here is just epsilon, right? So x plus epsilon is this point here. Well, I can write by the Taylor expansion, right, g of x plus epsilon is just g of x, right, plus epsilon times the gradient of g of x, right? And so now, because both points are on the surface, I know that this is equal to this, right? And in fact, they're both equal to 0. Right. And so therefore, if this and this are 0, then this thing here must also be equal to 0. Therefore, epsilon, and I should have taken the transpose over here. Epsilon transpose times g of x must be approximately equal to 0. Right? And in the limit, when epsilon goes to 0, then I get that this thing is exact. Right, so this epsilon is kind of parallel to the tangent here, and the vector here is orthogonal to that. Now, how are we going to use that? Well, the way we can use that is as follows. We're going to take a point here, XA, right? And we're going to say, well, suppose that I need to stay along this surface here. So if I need to stay along this surface here, then you can kind of think about this surface here as being the level set of some function, right? So g of x could be the height above a surface, right? And so when g of x is equal to 0, this is like being at sea level. So you might imagine something, a situation like this, where this is a 2D surface like the Earth's surface, right? And g of x is just describing height above sea level, right? So if I take, let's say, a cross section across here, right, and I look at g of x, then I might get something like this. So this would be g of x along that cross section, right? And then when I take this thing at 0, it's like taking sea level, so this is like water, right? And then the points here where it crosses are these points and these points here, right? And so remember, the gradient points in the direction going positive or going up, and so in this case here, if I was over here, the gradient might point up in this direction, which would correspond to, let's say, moving up the hill here. So you can kind of see that if I had a height above the surface that was given by this, where this is positive height and this is negative height, and then I filled the whole thing in with water up to sea level, then if this region was above the water, then I would get something like an island. So you can kind of imagine that this is the contour of the sea coastline of an island. The gradient's pointing up, so everything up here is land, right? So I'm going uphill, so this is land. I go downhill in the opposite direction, and that's going to be inside the water. So this is all going to be water here. So you can kind of think that what I'm trying to do is stay along the shoreline and yet get as close as possible to but make the function f as large as possible. So now the question is, well, suppose that I was trying to maximize some function, right? And maybe the function here that I'm trying to maximize is the volume of a bird, right? So suppose I'm standing on this island, I can only stay on the shoreline, but there's a bird sitting out here. So here's the bird. And the bird is singing, right? So the bird is singing a very nice song, and so I want to get as close as possible. I want to maximize the volume of the bird's song. So I want to get as close as possible to the bird, but the problem is I am going to have to stay on the island because I can't swim. So I can't swim out to the bird who's sitting out here in the middle of the ocean. Right, so how am I going to get as close as possible to the bird? Well, you can see here, well, if the bird was here, it's going to kind of be in this direction here. And I claim that this direction here is in the same direction as this direction over here. And how do I know that? Right. Well, suppose that I was at a point, right, which was on the island here, but was not the closest point. Right. So suppose I was like over here, right. Well, then in that case, in order to get to the bird, right, I would have to move in this direction, right? So the closest way for me to get to the bird is like this, right? So if I moved in this direction, the song would get loudest, right? This is the best direction I want to move in to make the sound louder, right? Now I can't move in this direction here because of the fact that this is going to take me into the water, but you can see that there's a little bit of drift when I move this way toward the left, right? So actually what I could do is make the bird sound louder by moving over here, right? I can't go into the water, but I can move, because this guy has a little bit of a direction in this direction, I can move a little bit over to the left, right? Just like if I was over here, right? To get to the bird, it would be like this is the direction of the gradient. And I can't move in that direction, but I could move over here and that would make the bird sound louder. And so when is the bird sound going to be the loudest it can be? I'm going to keep on moving over here, and only at this point here, where I'm exactly facing straight out away from the surface here, which is the exact opposite direction of g of x, the gradient of g of x in this case, then I can't move to the left and the right anymore. I just have to stay here and listen to the bird. Okay. So you can see here, well then, the gradient of the cos function here is going to be in the same direction as this, right? And it could either be in opposite directions like I've shown here, or you can imagine that, like, for example, if this was a lake, right? Maybe this is a lake. So the water's inside here, and actually a lake is not a good example, but suppose that this is going up the hill, and maybe the bird was up here. Right? So here's the bird uphill, sitting here. Right? But I have to stay on the shoreline, so I'm going to move along here, and so if I was over here, I would want to move a little bit over to the left. If I was over here, I'd want to move a little bit here over to the right until I get to this point here, at which point the gradient would be pointing in the same direction. The gradient of f and the gradient of g would be pointing in the same direction. Okay, so what that means then is that in order for these to be pointing in the same direction, they have to be able to cancel each other out. Right? So if I'm pointing in this direction, gradient of f, and I add some gradient of g, I can find some lambda to cancel these two out and get 0. And so in order to do that, I can either choose lambda to be positive or negative, depending on what I need. In this case, when they're pointing in the opposite directions, lambda would be positive. If they're pointing in the same direction, lambda would have to be negative. So using that fact, we can actually then set up the Lagrange multipliers right away. What we can say is, well, I'm going to define the Lagrangian function to be this thing, f of x plus lambda g of x. Right? And so now what you can say is, well, what's so great about this function here? Well, remember we have this thing here, right? So gradient of f plus lambda gradient of g. So if we actually take this thing and differentiate it with respect to x, right, I get gradient of f plus lambda times the gradient of g, and if I want to set this thing equal to 0, then I get the previous equation that I got before. Right? This one right here, right, which I want to solve. Also, I can differentiate with respect to lambda, right, this function here. When I differentiate this with respect to lambda, this thing goes away, and I just get g of x, right? And if I set that thing equal to 0, I get the constraint equation, g of x is equal to 0. So therefore, if I differentiate this Lagrangian function with respect to both x and lambda, right, then at the stationary points where that gradient is equal to 0, I'm going to get the maxima or minima of the function f of x with respect to the constraint. In fact, typically I'm not that interested in the exact value of lambda, right? And so in that case, I can just kind of eliminate it from the equations and not solve for it. So sometimes the Lagrange multiplier is referred to as an undetermined multiplier. So let's look at an example of this, which is shown here. So my function here is f of x1 comma x2 is 1 minus x1 squared minus x2 squared, right? So when this thing here is equal to 0, I get a line of length, circle of radius 1, right? But what's going to happen, this is kind of like a hill, right? In the center, when x1 and x2 is equal to 0, at this point here, f is equal to 1, right? And then when I move away from the center, x1 squared and x2 squared get bigger, and so I'm going to go down the hill. So this is kind of like a quadratic hill. And so I want to climb to the top of the hill, which is in the center here. So you can kind of think about this thing as being the bird is sitting here in the center. But the problem is that I am constrained to stay along this line here, the red line here, which is when g of x1 comma x2 is equal to 0, right? And so g of x1 comma x2 is given by this equation here. And so if I set that equal to 0, I can write that as x2 is equal to 1 minus x1. Right? Just set that equal to 0, move x1 and 1 over to the other side, I get this, right? So this is going to be a line with slope minus 1. Right? And it's going to intersect the plane right here at 1. So this intersection here is going to be 1. Right? And it's going to intersect over here at 1. Now, if I'm walking along here, then the closest I'm going to be able to get to the bird is this point over here, and so you can see this is kind of halfway between these 2 points. So this is going to be 1/2 and 1/2, right? So this, we can actually look at this thing directly now that we know this kind of picture, and we can pick out that, well, this is going to be the optimal point of the thing. Right? But let's try to solve that with Lagrange multipliers. So I'm going to optimize this function f of x1 comma x2 subject to this constraint, and so I multiply by lambda, so I get this equation here. And now I just have to differentiate this with respect to x1, x2, and lambda. Right, so when I differentiate with respect to lambda, I just get my original constraint back. That's this one here. Right, when I differentiate with respect to x1, this thing goes away. I get a minus 2x1 here, and then differentiate with respect to x1, this goes away, and I get a lambda, right? So I get a minus 2x1 plus lambda, and the rest of this stuff goes away, equal to 0. And I get, differentiating with respect to x2, I get this one here, minus 2x2 plus lambda, right, which we picked up by that. And now I can solve this thing, and when you solve it, you can see here that, well, if I choose x1 and x2 is equal to 1/2, right, and lambda is equal to 1, then I get minus 2 times 1/2, or minus 1 plus 1. So that's going to be true, this is going to be true, and I get a 1/2 plus 1/2 minus 1 is equal to 0. So all of these three are going to be true at this point, which is exactly the point that we had over there. And so that's a brief introduction to constrained optimization.